Hello, welcome to MAT 223 Engineering Mathematics course. In this course, we all study theory of differential equations. Our topics are basic concepts and initial value problems, and also we will cover existence and uniqueness theory. First of all, what is a differential equation? A differential equation is an equation involving derivatives of an unknown function. So there are some examples here. For example, in the first example, we see dy dx. This is the derivative of y with respect to x, and this is equal to 2 times sine of x minus 4y. Okay, so here we call x to be an independent parameter, and y is the dependent parameter or the unknown function. Okay, so in this example, we have one independent parameter x and one unknown function y and its derivative. So we have equal sign, that means we have an equation. Since this equation involves the derivatives, it is a differential equation. Okay, in the second example we have again the first derivative here, it's raised to the power fifth, and also we have second order derivative of y with respect to t this time, and our independent parameter is t in this time. Okay, next we see the third derivative of y with respect to x, and also the first derivative of y with respect to t. So it means we have two independent parameters. One of them is x and the second is t. So this is also a differential equation because we have derivatives and equal sign. So these are the other terms we have on the differential equation. Okay, so let's see also the last example. We have t here, x there, so we have two independent variables and one dependent variable y. So our differential equation is really a differential equation because we have derivatives of y with respect to x and t. Okay, so we see differential equation with only having independent variable x, and also differential equations with more than one independent variables. So let's see if we have their good names. So a differential equation is an ordinary differential equation ODE if the unknown function depends only on one independent variable. If we have only one independent variable, we say ODE or ordinary differential equations. Okay, so if we have more than one independent variables, like two or more independent variables, then we call the differential equation as a partial differential equation, so PD. Okay, so you'll see, you'll learn, you'll hear this word ODE most of the time in this course, but these PDs are not covered in this course, so this is just the definition to begin with. So example, the equation 1 2 and 1 1 1 and 1 2 are examples of ODEs. So let's see here, this is an ODE because we have one independent variable, and this is also an ODE because we have only one independent variable, and 1 3 and 1 4 are PDs because we have 1 and 2 independent variables, 1 and 2 independent variables, so it's more than one. That means we are working with PDEs on the equation 1.3 and 1.4. Okay, what is the order of a differential equation? So this is quite important. The order of differential equation is the order of the highest derivative appearing in the equation. Okay, so let's go back to our original examples and see what their orders. First of all, the derivative term is here. This is the only derivative in the equation. So what is the order of this derivative? It's 1, right? So we call this differential equation as first order differential equation. Okay, so in this example we have derivative terms this and that. So for this one the order of derivative is 1, and here we have order of derivative is 2. So this will be determining the order of the differential equation, and order of the differential equation is 2, we'll say. Okay, so the next one, this and that is that are the differential the derivatives. So we have the third derivative and first derivative. So the third derivative will determine the order of the differential equation, and we'll say the differential equation is the third order differential equation. Okay, so we have fourth here, first here, so this will be fourth order differential equation as well. Okay, and these are given already there. Okay, next we need to talk about the notation, how we show the derivatives. So first of all, this is the Leibniz notation for the derivative. So this is dy dx. This is really what we have seen so far, and this is the second derivative, and so on. For the prime notation, we have y prime and y double prime, y triple prime. After fourth derivative, we'll see in parentheses fourth, in parentheses 5, and so on. So the in general nth derivative, if n is greater than 4, we'll see y to the power like power y to the power in parentheses n. This will give us the nth derivative. Okay. A definition: any function phi defined on an interval I and possessing at least n continuous derivatives on I, which when substituted into nth order ordinary differential equation reduces the equation to an identity, is said to be a function, to be a solution of the equation on the interval. So the keywords are here. So this is the solution, and it's defined on an interval I, and it will has n continuous derivatives on I, and when we substitute this into an nth order ordinary differential equation, this will reduce the equation to an identity. Then we say this is the solution of the ODE on the interval. Okay, so this is basically whenever we have an equation and try to verify, we try to verify something is its solution, then we substitute this something into the equation and try to get an identity like 0 equals 0 or 5 equals 5 or y is equal to y. Then we say, okay, this is the solution. Okay, so this is the definition. Okay, an example: this phi is equal to 5 sine of 2x is a solution of the ODE given by this expression. And this is true because if we take the second derivative of this solution candidate, we will see the second derivative is negative 20 sine 2x. Okay, so if we substitute this into the equation with phi itself, we will see negative 20 sine 2x plus 20 sine 2x, and this will cancel out, this and that will cancel out, and we will see equals 0. Okay, so it will reduce the ODE to an identity. So this means we have a solution to the ODE like this. Okay. Secondly, if we have phi is equal to 3 cosine 2x this time and work with the exact same differential equation, okay, so is this really a solution as well? So let's see. If we take the derivative, we will see negative 4 will come out, and we will have a negative 12 cosine 2x. And then when we substitute this into the ODE, we'll see it's equal to 0, really. So this means, given any ODE like this, we have two different solutions. Okay, So this is the first one and this is the second one. Okay. So an ODE might have more than one solution. Okay. Let's see an example with a definition for what we call this sort of solutions. A particular solution of an ODE is any one solution. If we have any one solution to the ODE, we say we have a particular solution. Okay. The general solution of an ODE is the set of all possible solutions. Okay, so this is important. Particular solution is only one solution that will satisfy the ODE. When you substitute into the ODE, it will reduce the ODE to an identity. And the general solution is the solution set which involves all possible solutions. Okay, so this is the general solution. Okay, example, for any arbitrary constant C1 and C2, these constants might be 1, 3, 5, 6, pi, 1 million, whatever it is. So these are just constants. Say psi is equal to C1, the first constant, times sine 2x plus C2 cosine 2x is the general solution to the ODE. This one. Okay, you can verify this fact just by substituting the solution into the ODE and see if you really get an identity or not. So this is the way to show it's a solution. How we can show it's a general solution is a matter of the future lectures. Okay, so you just need to believe me, this is the general solution to the ODE given by this expression. Okay, so an nth order ordinary differential equation in one dependent variable can be expressed by the general form. So this is supposed to be independent variable. So this is not a dependent or independent variable. I will correct this in your notes already. So let's also put independent here. Anyway, okay. So this is the general form. Okay, so the general form will involve y and its derivatives and x. So it means we have a function of all these input values. So we can see, for example, y squared e to the y prime sine 2, for example, sine 2 y double prime, or the 5x, whatever it is, just function of all these terms. So this means we can create any algebraic function, I mean any algebraic term with that, and it will give us a differential equation. And this is the general form of the nth order ordinary differential equation. Okay, so let's say we can solve this equation with respect to yn, y, the nth derivative of y. So let's say we can really separate this guy from the others. So when we do that, the expression, the general form, will be looking like this, and this will be called as normal form of the ODE. Okay, so the normal form of the ODE will look like this. Okay, so the highest order derivative will be on the left hand side, and the rest of the terms will be on the right hand side. Okay, also a definition: a solution in which the dependent variable is expressed solely in terms of the independent variable and constants. It is said to be explicit solution. Okay, explicit solution means we can separate the dependent variable from the independent variables and constants. Okay, so it will look like this. So say this y is the dependent variable and x is the independent variable. Then we can write the solution as y is equal to phi of x. So on the right hand side we will only have phi of x. Okay, on the other hand, a relation k of x comma y is said to be an implicit solution. In some certain problems, we'll see we cannot solve for y in a relation like this. Okay, so we cannot really write the solution y is equal to this and that. Okay, so for this reason we need to introduce implicit solutions of an ordinary differential equation as well. So explicit solution, whenever we can write it like y is equal to f of x, for example. Implicit solution will happen if we cannot separate y from the others. Okay, so these are the definitions. Let's see in an example. Actually, we cannot separate, might not be a good phrase for that. So we might, we can sometimes, yes, we can also separate it from the others, but we don't do that as well. So this might be the option as well. So for example, let's see in an example. So x squared plus y squared is equal to 25. So in this example, we can really isolate y from the others, and we can solve for y, right? This is something we can do, but in reality, we didn't do that. So the options for implicit solution is are first, it has to be implicit, so it has to be given that way. Or the second option is we can really make it explicit, but we just put it implicitly. Okay, so this is a good example for that. So we can really write it explicitly, but we leave it implicit in an implicit form. So x squared plus y squared is equal to 25 is an implicit solution of the differential equation. This, how can we verify that? So if we take the derivative with respect to x on the both sides, we will see this is happening, right? So the derivative of first term, second term, and after the equal sign. So we'll see this is 2x plus 2y dy dx. You need to be familiar with the implicit differentiation like this. So this is the chain rule. 2y times dy dx, and this is equal to 0 because the derivative of a constant is equal to 0. So if we organize that and do some algebra, we'll see dy over dx is equal to negative x over y. So we started with this solution and we ended up with that. So this really is a solution. Okay, an nth order ordinary differential equation is said to be linear if f is linear in all of these terms. These terms are y, y prime, y double prime, and all the, I mean, all the y and derivative of y. So this is the set of all the variables that has to be in linear uh, in order to have a or linear ordinary differential equation. Okay, this means that an nth order ODE is linear. Then we write it as this form. So a linear differential equation will look like this. So we have the nth derivative of y, n minus first derivative of y, and first derivative and y itself. So if we check all these terms, the coefficients of these terms has to be at most a function of x. So what does this really mean? At most a function of x means it can be constant or a function of x, but it cannot involve any y values. For example, if we have anything with y, if we had anything with y there, then we wouldn't be working with a linear equation. Okay, so linear means this y to the n terms or all these terms will have at most a function of x coefficients. Okay, so this is the key. And of course on the right hand side we will have g of x, and if anything with y would involve here, that would be coming to the left hand side, so we can isolate it from there. Okay, so in particular, this is a first order linear ODE. Because we have y prime and y, the coefficients of all these terms are at most function of x, at most function of x, so then we say this is a linear ODE, and also this is first order because the highest derivative is 1. Okay, so let's see the second example. We have also second order ODE, first of all, because we have the second derivative at most, and also their coefficients, this one, and that one, are all at most function of x. So we say this is a second order linear ODE. Okay, this is very useful classification. Okay, some certain examples with coefficients as well. So this is the coefficient of y prime, so this is at most a function of x. This is the coefficient of y, so this is at most function of x, and this is the right hand side. So this is a first order, because we have first derivative, first order linear ODE. Okay, for this one, the coefficient of y double prime is x cubed, so this is at most function of x. This is at most function of x. This is at most function of x. Then we say second order linear ODE. Okay. Another definition: a system of ordinary differential equation is two or more equations involving the derivatives of two or more unknown functions of a single independent variable. So this is the key point here. Two or more unknowns function. If we have more than one unknown functions, then we have a system of ordinary differential equations. Of course, it has to be with a single independent variable, otherwise it will be a system of partial differential equations, right? So this is what we really need to point out. A solution of such system is differentiable function like that, functions like that, and these functions are defined on a common interval I, and they satisfy the system of ordinary differential equations. Okay, so y1 will be something like that. This is the solution for y1, and y2 will be something like that, and so on and so forth. All these terms, all these functions has to be defined on a common interval I, and they need to satisfy the ordinary differential equation. Okay, an example: if x and y denote dependent variables and t denotes the independent variable. So x is the unknown function now, y is also unknown function. Okay, t is the independent variable, and then we say this is a system of ordinary differential equations. Okay, so why is this so? Because we have two unknowns, x and y, and t is the only independent variable. So this is a system of ordinary differential equations. Okay, so we are often interested in problems in which we seek a solution y of x of a differential equation so that y of x also satisfies certain prescribed side conditions. Okay, that is, conditions that are imposed on the unknown function y of x and its derivatives at a point x naught. Okay, so this is what we really have in initial value problems. So if you're working with an ODE, it needs to satisfy for certain applications, it needs to satisfy some extra conditions, like the initial condition. Okay, so for example, if you put some cake, if you take a cake out of oven and put it on a room, its temperature will start decreasing, right? Okay, so this will introduce a differential equation. Okay, so the initial temperature of the cake is really important because you know the the higher temperature it starts with, the the slower it will take to reach the equilibrium temperature for that cake. Okay, so this is very important. Now we will see also. So we will see the differential equation and also some initial conditions like that. So for this particular problem, we'll say this is an initial value problem, IVP. Okay, so an initial value problem can be prescribed like that. So the key point here is each each additional condition has to be given at the same point. Okay, so x naught is the same point. Okay, so this is the initial time or initial position or whatever it is, but they all has to be given at that point. So then we called it as initial value problem. Okay, so this is an initial value problem. The derivative is f of x comma y, then y0 is equal to y naught, and this is an initial value problem because we have given an initial value, and also this one is a initial value problem, and this time we have second order initial value problem because this is, as you see, the order of the differential equation is second, and for this particular case we need to have two initial values, and this will be the first one and this will be the second one. Initial value at the initial value for the function itself and initial value for the derivative of the function. Okay, so if this was not given, then we could still say this is an initial value problem, but we would have some problems with the uniqueness of the solution that we will see later on. Okay, so if we are given a solution for example, for this particular ODE, so this is y prime is equal to y, so this means this differential equation means the derivative of the function is equal to itself. So which function is this? We can really predict the solution. So solution will be c times e to the x, because whenever we take the derivative of this function, we'll see it's equal to itself, right? So y prime is equal to c e to the x. So this is equal to itself. So this is the solution. And also we are given an initial value. So y0, y of 0 is equal to 2. So this is the solution of ODE, but not the initial value problem, because we need to consider the initial value as well in order to make it the solution for the initial value problem. So to do that, we need to substitute 0 for x and 2 for y. And when we do that, we will see the constant c is equal to 2, so y is equal to 2 e to the x is really the solution for this initial value problem. So this is the initial value problem with initial condition, and this is the solution because we found the solution for ODE first and then substitute the initial value to identify what value of c really makes this initial condition happen. Okay, so an example for second order or initial value problem. Here we have an psi function, and this psi function is really the solution for this particular ODE. We have seen that already, right? Just a minute ago. So here we have the solution to the ODE. But if you make it an initial value problem, so if we have initial conditions for this problem, then what really happens? We need to substitute, for example, pi half for x and 2 for y in this, or the solution, to see what we really get for C1 and C2. Also, we will do the same for the derivative. We will take the derivative of this function, okay, and then substitute pi half in the derivative of this function for x, and -6 for the derivative of this function, and we'll see what is C1 and C2. Okay, so this is the strategy. Now, substituting x equals pi halves and y is equal to 2 in psi, we will see 2 is equal to C1 sine pi plus C2 cosine pi. Okay, we know sine pi is basically equal to 0, so we can eliminate this. Cosine pi is -1, so C2 will be -2. Okay, so once we find that, we can substitute C2 in the solution, and we say, okay, psi is equal to C1 sine 2x minus 2 cosine 2x. Okay, so this is already found. And we need to take the derivative to use the second initial condition. When we take the derivative, we'll see this is happening. Okay. Then when we substitute pi halves for x and -6 for the derivative of y, we'll see this will come out, and then sine pi is 0 again, and cosine pi is basically what? -1. So -1, -2, -6, so C1 will be 3. Okay, so this is 3. Okay, now we found the C1 as well, and C2 was there already, so we say the psi is equal to 3 sine 2x minus 2 cosine 2x. Okay, an example for initial value problem with more than one solution. Okay, each of the functions y is equal to 0, okay, and y is equal to 1 over 16x to the fourth satisfies the differential, actually this should be satisfy the differential equation that, okay, each is there, so it has to be satisfied. That was correct. Okay, each of the functions satisfies this differential equation. Dy over dx is equal to xy to the 1/2. So if you substitute 0 for 0 in this differential equation, you'll see the derivative of 0 is equal to 0. So 0 is equal to 0, right? So this will reduce this ODE to be an identity. So this is a solution. Also, this satisfies the initial condition, because y is equal to 0 means y is 0 everywhere, so y is 0 at the 0 as well, so this will be satisfied. And also, if you substitute this into the ODE, you'll see what the derivative is equal to 1 over 4x cubed, right? 1 over 4x cubed, and here we have x times 1 over 4x squared, because the square root of this function is 1 over 4x squared. If you multiply that by x, you'll see we have 1 over 4x cubed, and we know this is also 1 over 4x cubed. Then we can say this will reduce this ODE to an identity. Okay, let's also see if we can really if this will really satisfy the initial condition as well. So if you substitute 0 for x, you will see y is equal to 0. So this is also satisfied. Then we have an ODE and its two solutions. Okay. So then problem arises: does a solution of a problem exist? Like initial value problem, given any initial value problem, can we really find a solution? Okay. The next thing is, if a solution exists, is it unique? Okay. So this question will be answered next. Existence of a unique solution. Let R be a rectangular region in the xy plane defined by this, okay, and it will contain x naught y naught in the interior if f of x and the derivative of with respect to y are continuous on R, okay, this is the condition, then there exists some interval I naught which is involving x naught in it, and it's small enough. I mean, it's really an interval, and it's also in the 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 interval for x, and a unique function y of x defined on I naught. That is the solution of the initial value problem. Okay, so key points: a rectangular domain, the function f, the right hand side function f, and its y derivative has to be continuous. Then we have a unique solution. Okay, so let's see what was wrong with this problem to not having any not having unique solutions but two. So this problem with that was, if we take the y derivative of this function, I mean the right hand side function here, you'll see it's not continuous at 0, or even for function itself, I mean f of xy. If you consider 0 0, I mean the initial value is 0 comma 0 here, right? So the initial value will be 0 comma 0. So if you substitute 0 comma 0 here, and you'll see this function, this is really a square root of y. If you graph it, or if you can imagine, this root function is not defined on the negative side. Okay, so this means this function is not continuous at 0. Okay, so this was the problem. For this reason, we have two solutions to the initial value problem. Okay, but if we have anything else, like any function, any ODE with the right hand side function is continuous with its continuous y derivative, then we say it has a unique solution. Okay, that's all for today. Thanks for watching.